3.1, introducing derivatives. So what we're going to do is go back to the tangent lines that we did in 2.1 and talking about average and instantaneous velocities. So we're talking about tangent lines, the instantaneous one. At one point, that line that's tangent to that point on a curve. And then we can look at the slopes. So obviously in this first example, our slope is negative. And then in our second example here, we have at this point, though, same curve, our slope is positive. And the whole reason we do this is because tangents give direction of the motion, trajectory of an object or something. So, for example, in this picture, we have that it's got a direction of this following that tangent line. And as it's moving, our tangent lines can change, and we can have showing the different motions. So the slopes of the tangent lines as they change along a curve are the values of a function called the derivative. If a curve represents the trajectory of a moving object, the line tangent to the curve at a point gives the direction at that point. All right. So then if I go back to if a picture of a trajectory, I'm going to draw one real quick, and then I want to say that if I have say this point P and the tangent line to it, didn't draw it real good. And then the next thing I want to do is say, okay, let's zoom in on just this point. So just in this box, if I want to see this tangent at this point, it's kind of maybe getting a little smoother, it flattens out. We call this linearization, the local linearity of this point. So this P, as we zoom in, gets straighter and straighter and straighter, or, in a sense, is the tangent line at that point. So that's what I want to talk about, is going in and talking about this instantaneous, at that instant. We want to know how quickly F is changing at that point, instantaneous rate of change. So going back to the definitions from earlier, we have the secant slopes are between 2 points. Notice on the interval from A to X, we just have 2 points and we use the slope formula. Instantaneous rate of change of F at A, we're still using it, but we want to use the tangent line. So we're going to say, okay, we're trying to approach that A value, so we're taking the limit of it. So we want to take the limit of this slope, saying we're approaching the tangent line. Notice that we can also write an equation of that tangent line using, and they have point slope formula here. Remember, I'm always going to rewrite it as this. It's going to be the slope of the tangent, x minus that A, and I'm going to move that f of A over, which does not fit on my board here, but that y value, or f of A, I move to the other side. So I get more in that y equals mx plus b slope-intercept form. All right, on here, I want you, if you want to follow through on the book, I'm actually going to bring in another example, which is number 10 from the homework section. If I'm given this equation, and I want to know at the point P, 1 and negative 7, I want to know the slope of the tangent line to the graph at this point, and then I want to find an equation of that tangent line. So I'm going to go ahead and do the process that we were doing earlier here. The slope of the tangent line, which is equal to the limit. And obviously I want to approach A, or in this case, my 1 in my point. That's what I want to approach. So what I'm going to do is I'm going to have f of x, which is just this function with the x's in it. And that's going to be all over the x. That's my first point. Then taking the difference from the second point, I really want to have minus f of A. And when I do that, if this is my A, this is my f of A, and it turns out it's already calculated for me. It's negative 7. And then I have to have minus my a down here, which is 1. And then what I want to do is, if I did direct substitution right now, I'm undefined in the denominator. So I'm going to go ahead, try to work through and simplify this one, and then see if I can go ahead and do direct substitution. So I want to go ahead and continue. Simplifying the numerator. Combining like terms. From this point, I'm going to have to see if the numerator factors and if I can reduce the x minus 1 out of it. Remember, with factoring, you could do the ACB method, and if you don't remember that, you've got to see me. The numerator does factor into a negative 3x, and because the last term's a positive 8, the numerator does factor into a negative 8 and a negative 1. And then I see here that this reduces. I no longer have an undefined issue going on. I'm going to go ahead and do direct substitution. And then I can see I have negative 3 minus 8, or negative 11, is my slope. So I'm going to use this slope and the point they gave me to write the equation of the line. So I'm going to go ahead and plug into my formula, point slope formula. My negative slope, my point was 1 and negative 7, and then I'm going to go ahead and simplify. So I have the slope of the tangent line and the equation of that tangent line. The next example in the book is from a table. And before I get into this definition, I want to go ahead and look at this table more. Last year on the AB exam, you were given a table and you had to find the instantaneous rate of change for something. And this is the exact same example that you saw on the AB exam. Remember, there's different ways to go about it. This book tells us, well, there's 3 ways. Given a chart, you can still try to find that instantaneous rate at a point. The example in the book walks through when t is 6, or for June. But if I want to go ahead and try to use the examples from homework, I'm going to do number 15. And it's saying, using the same information, do September. Try to find a good guess on the instantaneous rate that the Facebook is growing in September. So what I want to do, there's 3 ways they said. So 1, I'm going to go ahead and use September, which would be 9 and 457. And I'm going to use an endpoint on the immediate side of it to this side, which would be the point 6, 417. And I'm going to go ahead and find slope. And if I did that, the slope for this one should be 13.333. And then they said, okay, another way of doing it is using that same point that we want to approach, but using the point on the other side. So I'm going to use 12, 483. From here, if I do slope, I would get 8.66. And that's obviously not real good to make a guess from either one. So then they said a third way, which is the way I taught you guys last year, was to go ahead, if I want to know the instantaneous rate of change at 9, I'm going to use the points on either side. So I'm going to go for the third method. I'm going to use 6, 417, and 12, 483. And I'm going to go ahead and figure out the slope from here. And I see that the slope on this one turns out to be 11. That's kind of in between this slope and it makes the most sense. Then this is probably the closest guess that I'm going to get to the instant rate of growth when we are looking at September. All right, going on then. The book then gives us this picture and the alternative definition for rates of change. So what's the difference is I've got this H in there now. Why? Well, remember, I'm trying to use this difference quotient. We saw this earlier, but this difference quotient is saying it's some value H that I'm trying to get as close to that A as I can. I'm hoping that H goes towards 0 and I can actually hit A. But I can't take the difference of f of A and f of A. It would be 0 over 0. It would be silly. So I'm hoping this limit of where this H is going to approach 0 so that I can get as close to this value of A as possible. Remember, this is called the difference quotient. The only difference is we have this A plus H in here. And it's going to be over H because it really was two slopes, 2 points, f of A plus H over A plus H, and then minus f of A minus the A. The A's reduce in my denominator, and I just get H. It is still slope of 2 points. So then I can go ahead and do all the algebra that we've done before in these types of problems. All right? So here, this is the one in the book, and they do walk through this one. I'm going to do a different one from the homework section. I'm number 19. If I'm given this function, f of x equals x squared minus 4, and the point P where it's 2, 0. Remember, this is really saying A and f of A. All right. So going back to this, let's use this new alternative definition of limits as h is approaching 0. Notice I have, wherever there's an x, I'm going to plug in A plus H. But because this value here, my point is A, I'm going to plug it in. I don't have to. I could do it at the end if you want, or you could do it now. But I have the A plus H, plugging it into my x in this first point. Then I'm doing f of A, which is this value, so I'm just going to have minus 0 over H. Then from here, I need to simplify. I need to reduce this somehow, because otherwise I'm undefined. So I'm going to go ahead and I'm going to expand this top numerator out. I'm going to first term squared, multiply the 2 and double it. Last term squared, don't forget the minus 4 at the end, all over H. From here, we can see that the 4 is reduced. From here, if you wanted to, you can factor GCF of H out and then reduce, or go like this. And then you can see at the end here we have, oops, got my limit. The limit as H is approaching 0 of 4 plus H. I can now do direct substitution and see that I have a slope of 4. Then they want us to go ahead and find the equation of the line again using the slope and that point, and we should get y equals 4x minus 8 for the equation of the line. So here we're formally giving the definition of the derivative. The derivative of f is the function. Notice it says function. So I have f prime of x equals the limit of the difference quotient as h is approaching 0, provided the limit exists and x is in the domain of it. F prime, or f derivative of x, exists. We say it's differentiable. If f is differentiable at every point on an open interval, then we say f is differentiable on that interval. Note, f prime is called differentiation. The process of finding it is differentiation. And to differentiate f means to find f prime. All right? So then I have, for example, 4 from the book, which is going way back to 2.1, where we were first talking about instantaneous rates of change. But I want you to do a different example from the book. So, or from the book. So I just made one up. We're going to do f of x equals 2x squared plus x minus 1. All right? So they want us to just go ahead using this new definition of limit for derivative with a difference quotient and just going ahead, and then I'm going to plug in some values to evaluate. So I'm going to go ahead and say f prime is equal to the limit as h approaches 0 of this function. Uh-oh, sorry, wrong. Where I'm going to plug in, and I'm just going to use x. Our definition had x plus h rather than a in wherever there was an x. That's the first point. N minus just the value of that function again, or just what I have here, f of x. So 2x squared, I'm running out of room, guys, plus x minus 1 all over h. All right, from this point, we have to do all of our algebra. So I will continue here and say, it should work out to 2 times doing my squaring inside. Oops, left that one there. Distributing my negative here all over h. Oh, I forgot my limit. Then keep going. Combine like terms. These reduce. The x's reduce. The 1's reduce. And then I'm left with the limit as h approaches 0 of 4xh plus 2h squared plus h over h. Do a GCF of h, or if you can, from here you can simplify into each term of the numerator. It reduces that one of those, and this becomes a 1. So now I'm left with the limit as h approaches 0 of 4x plus 2h plus 1. Do my direct substitution, and I've got this is my f prime, my derivative of f. From here, if I wanted to evaluate, remember, if I want to evaluate, this is a function. It still has that function notation. With prime, it's a derivative function. So if I want to evaluate it, I can do this notation, and it means plug into for the x in the derivative. So in this case, I have this, and my slope at this for this graph, when x is 2, at the point 2, it has a tangent line slope of 9. Same function, if I want to do a different point, say negative 1, I plug in a negative 1, and I have a slope of negative 3 there. Notice then, if I want to plug in, and I'm going to pick this one in particular, negative 1/4, plugging this in, I should have a slope of 0. Whatever this function ends up being, these are the different points, tangent line slopes. So I had 2 positive slope. If I was at negative 1, negative slope. And this last one, when slope was 0. All the different points, the same graph. All right. Notation. Basically, they did it with the delta for change. So instead of h, they're saying it's the change in x's. However, the x value is changing, which we're hoping approaches 0. So then they replace that. Instead of h, they have the delta x. It's just that how we want to get close, how are the x changing as we get closer to the value we really want to evaluate at that point. It leads us to the dy dx notation. Remember, dy dx is read the derivative of the y with respect to x, or dy dx. It does not mean dy divided by dx. It is a reminder of the limit in the changes in y's over the changes in x's. All right, so in addition to this notation, f of x or f prime of x, or the dy dx, common ways we could do the df dx, we can do this notation here. This one and this one are usually ones we see. This one right here, we don't usually see with us. All right? Remember, the other thing is some people use this notation dy dx. Instead of plugging f prime of 2 in and plugging to evaluate a slope, they may use this notation to evaluate. A derivative calculation. So on this examples, they want us to go ahead, find the derivatives. In the book, they may give us a point or not. But I'm going to go ahead and do an example from the book, homework sections 49. The function is f of x is equal to the square root of 3x plus 1 when a equals 8. From here, I want to go ahead, find my limit using the definition that we have when h is approaching 0. I'm going to go ahead and do that same thing. Wherever there's an x, I'm plugging x plus h in. And then from here, just the function all over h. Long story short, you have to multiply this by its conjugate of the numerator in order to reduce and get rid of that h in the denominator. We should get down to, when you do all the algebra, 3 over the square root of 3x plus 3h plus 1 plus the square root of 3x plus 1. At this point, there is no issue with plugging in 0 for the denominator, and we get 3 over 2 of the square root of 3x plus 1. Then if I want to, they said, okay, use this point when a is 8. Really, they're saying when it's 8, and you would plug in 8 into the function, and we get 5. So I'm going to use that point. We're going to use this derivative for the slope, find slope in the equation of the line. So slope should end up being 3/10. We're going to use the point 8,5 and write an equation of a line. That should be y equals 3/10 x plus 13/5. So it would be the same process again. All right, one more that I wanted to do with you guys. I'm going to do example 52 from the homework section, where f of x is equal to the hyperbola 1 over x, and we want to do when a equals -5. So remember, that means we're really doing the point -5, -1/5. And then we're going to go ahead and do the limits again. For this one, I just really wanted to quickly review the algebra for this, because this is what I'm plugging in. Wherever there's an x, I'm plugging x plus h for the first point, and it's all going to be over h. And then you're going to have to rationalize these denominators. I'm going to multiply or make this all the numerator one expression. So I'm going to do this real quick. Since it is being divided by h, long story short, you do realize these two then, when you multiply by its reciprocals, it becomes this. And this is the one that I want to go ahead and simplify. Long story short, we should get this for our derivative. And plugging in 0 for h, we should get x squared. And then you're going to go ahead and find the equation of a line.